right, everyone. Good afternoon. It's 2:30 p.m. I know because I was waiting patiently. Anyways, how's everyone doing today? Okay, bad. All right. All right. This is my kind of first time, so go easy on me. Today we're going to be talking about tries, lecture 15, which is a very exciting subject, I would say. So first, some administrivia. First of all, your midterm is out now. It was released today. So those are going to be due Monday, end of day. We're not going to accept any late assignments for your midterm. So we're not going to accept any late midterms. Even if you have late days saved up, you can't use those. Also, the midterm, I wouldn't stress about it too much. It was designed to be done in about an hour, like 2 hours tops. So yeah, don't sweat. Just try to give it an honest effort. I'm sure you will all do fine. Also, exercise 3, that's due today if you haven't done it yet. Project 2 was due Wednesday, but we're accepting late submissions until tomorrow. So try to get that done if you can. Oh, also, if you haven't noticed, I'm not Casey. Casey isn't here during lecture. I kidnapped her. No, I'm joking. I'm actually Sonia. I'm filling in for Casey today because I'm going to be teaching 373 in the summer. And if you want to be a TA, you can apply now. I believe I sent out a message on the EdSTEM board, and it should be pinned. So fill out that Google form, that TA application. And don't forget, if you do want to TA with me, not only do you have to fill out that application, but there's another application as well, the actual common TA application through the CSE website. If you want to find that, just Google search TA UW CSE applications. It should be out now, those applications. I think they came out a couple days ago, so make sure you fill those out as well as the application I filled out, which is the Google form. Okay. Enough about me. Let's get into the fun stuff. All right. So a little bit about the try data structure. It's a really, really cool data structure that I would say is really helpful on interviews, especially with letter parsing or character parsing and sequencing. It has a lot of good real-world applications as well. Again, if you're into natural language processing and the separation of characters and words in a string, then the try is really, really important. It's a really powerful tool, really fast, effective. So let's get into it. All right, a little bit of the introduction. The try. All right, it's basically a specialized data structure, okay, and it holds a sequence of characters. All right, hopefully in your try, you're going to have a lot of shared sequences of characters. So we call these common prefixes, right? Words that share the same beginning characters in it. So for example, if we have this set ADT, which by the way, in this lecture, we're going to be implementing the try using a set instead of a dictionary, but you can use a dictionary or a hash map, whatever you want to call it. So here we have an example set ADT with the words sap, sad, alls, a, same, and sam. All right, and on the right, we have a try representation. If you catch me saying tree, just think I'm saying try for the purposes of this lecture. It's really interchangeable, but try. So this is the try representation of these words. You can see how for the word sap, we go down, we see we have S-A-P, so we sequence out the characters of sap, and that's how we have sap in our try. Same with sad, S-A-D, alls, a, same, all the way down here, and then sam. All right, so that might look a little funky, but let's go through how we actually read this try representation, how we understand it. So each level of the try, this should say try, represents an index in the string. So this first level of the try, we can see it represents the first letter in every word of our set. So just based on this first level, we can see that all the words in our set will either start with the letter A or the letter S, right? then we can see that the children at the level represent every possible character that we can have at that index. So for example, if we go down the left path, we go down the index A, right? So if our first letter is A, we look at all the words in our list that start with the letter A, we can either, the only possibility that we can have for the second letter of our word from our list is W. We have to have AW as the prefix of our word for every other word in our list, right? If we go down this path A, right? If we go down this path SA, right? So the first two letters of our word is SA, then our possible children for the third character in our string can either have the letter D, the letter M, or the letter P, right? So we can either have sad, sam, sap, or same, okay? So here we can see that this abstract trie stores the set of strings alls, a, sad, same, sap, sam, as we mentioned before. But what if can we have the word aw? I mean, we have it in our trie, like AW, and we hold the letters in there. So why isn't that like a part of our list? Why can't we consider that as a part of the list? Well, the way that we deal with this difference is we mark which nodes complete a string. So which characters are the last character of a word in our set if they're purple, right? So A is the last letter of this word, A. It's the only letter, right? So that's how we know it's a word. But aw, right, AW, well, W is white, so it doesn't end any string in our set. That's not a word in our string. Whereas alls, S is purple, so that means, yep, that is a word, right? Alls, the path to this last node, this purple node, this path from our root to this node is a word in our trie. All right, so some examples with working with purple nodes, as I like to call it. Let's see, for example, we have this input string, Sam. All right, is Sam in our trie? Let's see, we go S-A-M. The last letter is a purple node. Sam is in our trie. What about S-A? S-A, we end on a white node. Nope, that's false. What about A? Again, purple node. Sakwa? Sack? All right, so we go S-A. We look down. We don't have a Q. All right, so we kind of fall off the edge. All right, so that is a false. All right, so there's really two main ways where we can fail a contain, right, to check if there is a word in our trie, and that is if the last letter that we end on isn't purple, right, the last letter that we try to search for in our input, if it's not purple, that's a fail. If there's some letter in it when we are trying to search for it, if that's not in our trie, if we fall off, then that's also going to fail. All right, so I personally love examples, all right, and my name is Sonia, as I mentioned before, and I'm not sure if you guys know Sonic the Hedgehog at all, but this is my favorite character, Sonia the Hedgehog, and I'm just going to use this example with Sonia and Sonic. All right, so let's say we had a set of our favorite hedgehogs, Sonia and Sonic, and we want to put them in a trie. Well, first we would go down our trie and we'd put in our input letters, right? So we put in S, O, and I, right? So Sonia and Sonic both share the same common prefix of Sony, S-O-N-I, but the last letter in both of these names is different. So that's when we start to branch off. So Sonia goes off and branches off to this last A node, marks it purple because that's the last letter in her name. All right, so Sonia, that is a name. And then Sonic branches off and creates a C node, marks it purple, saying he exists in the set. That's Sonic. All right. Another example, because I learn best with analogies, and I'm sure a lot of other people do too. So think about tries as walking a path, or like finding words in a trie as walking a path. So who here knows The Wizard of Oz? Yellow Brick Road? Some people, maybe? Okay, yeah. All right, we got some people. Awesome. So think of it as like the yellow brick road from The Wizard of Oz, where instead of following a yellow brick road to, the end destination, which is The Wizard of Oz, you think of it as a letter brick road. So each brick in the road is a letter in the name or the word that you're trying to search for. And your end destination, oh, someone was gonna drop something. All right. Your end destination is the final character in the word that you're trying to search for. All right, so, okay, for example, I'm not sure how loud I can talk walking, but for example, if I was trying to put everyone here's names, first names, into a try, okay, I would start with my own name, so S, right, I walk the brick, S, right, this is the S brick. Everyone else in this room whose name starts with the letter S will be on the same brick as me, right, our name starts with the letter S. Then I would be like, okay, where's O? All right, I walk on O. Everyone whose name starts with the letter S-O, again, same brick as me. All right, then from the O brick, I go to the N brick. I go S-O-N, S-O-N. Everyone whose name starts with the letter Son, or S-O-N, same brick as me. Then from the N to the I to the A, so I stop, mark the node purple. I walked the path of Sonia. All right, so everyone else whose name is Sonia in this class will be in the same brick as me. All right. Now, if we had someone whose name was like Sonia Qua or whatever, like someone whose name ends with the letter Q, right after Sonia, then they wouldn't stop at the A in Sonia. They would continue, right? They would continue one brick after and stop at Sonia Qua, the Q in Sonia Qua, all right? Even though we'd share that same prefix, Sonia. Okay, so think of the keys in a try as a sequence of characters. So normally in dictionaries and hash maps and, a lot of the ADTs that we've learned so far in 142, 143 in this class, they all treat their keys as one big, atomic blob, one big key that can't be separated into smaller subcomponents. It's just like the string, for example, that's the key. But tries are really cool because you can actually sequence the characters. So strings are made up of characters, right? So it's not just one big string, it's multiple little characters that make up that big string. All right, and the characters don't even have to come from the Latin alphabet. So the character includes most Unicode code points. So like this word for cake in a language that is not English, that could also work, right? You separate it by each character. Elements in a list, right? It doesn't have to be a character type. It could be elements in a list type, and each element is its own, character or subcomponent in a sequence. Same with bytes, right? Binary data or binary information, you could just separate it into different bits, and that's your sequence. So tries are defined by three main types instead of two. One is the alphabet, right? So the domain of the characters that you can use, the total possibilities of the keys that you can use or the strings that you can have. Then there's the actual key, right, which is the sequence of characters from the alphabet, like I guess the strings in your list. And finally, it's the value, right? We're not going to really focus on the value too much for this class. You can ask about it, but since we're using a set implementation, we aren't going to focus on the dictionary implementation too much. But if you were going to use a dictionary value, you can also have value. So for example, in the Sonic and Sonia the Hedgehog example, if my favorite hedgehog was Sonia, then I would put her ranking, I would put her value as 1, and then Sonic the Hedgehog, I would put his ranking as 2, my second favorite. That would be his value. All right, so now let's talk about the implementation of the try data structure. This looks kind of confusing. All right, I hate looking at code, but if we look at it line by line, it's actually not that bad. All right, so the first line is just the root, right? For the try set class, the first one is the root. That just refers to this, root here. We don't really need to put anything. It's just empty. It's just a root. Then we have the actual node class. So what is the information that we're storing in each node? Well, we have to store what character each node represents, right? So each subcomponent in the sequence, that's each character. Then we have the Boolean is key. Is it purple or not? Right? Is it the last character of a word in our try? And then finally, the private map or hash map, which connects the character, right, our current character, to the next nodes, its children, essentially. So for this A node, its next map would just have this node W in it. Right? For this A node, it would have D, M, and P. It would have 3 nodes, so its map would be of size 3. All right? Are there any questions about that so far? Or should we? Yes.
Yeah, could you briefly explain again, like, what are the map fields of each node?
Yeah. That's a really good question. Sorry, can you say that last part again?
Yeah, it's just like, because like, if you have one node that branches into 3, how does that work?
Yeah, so if you have one node that breaks into 3, that's a really good question because our example doesn't cover that, but essentially we would have 3 values in our map, right? We'd have 3 nodes in our map where each of those 3 nodes is like a child. Does that kind of answer your question? Okay, awesome. Yes.
Do we have to use the map to link to the next, or can we use like another try or like a hash set?
You could, that's a really good question. I'm not sure how that implementation would go. I guess you could use a hash set, yeah. You just say like your next character is L or B or whatever. Yeah, that'd be cool. Yes?
Yeah, does each map only have 1 key?
Does each map only have, yeah, it has to have 1 key, and that 1 key represents the current node. Yeah. But it could have multiple values, or it could have no values, you know, if it points to no children. Yes?
Is there a limit to the number of nodes you can have branching off of one node?
There is, I mean, I guess it's like, you know, the maximum number of characters in your alphabet, right? You can't like add more than what there is in your alphabet, especially because every string should be unique, right? So you can't have more than one of the same. Any other questions? Oh, yes.
Question, I'm interested when you talk about these try that you want to include all people's name in this class, the note rule, they should have a lot of child children, right?
Wait, sorry, can you say that again?
I mean, for this try that, if you want to include all names in this class, so you should generally have all alphabet from A to Z, so
Mm-hmm.
rules should include a lot of children, right? A, B, C, D countries.
So if you're, let's say you had a set of names that, you know, started with every letter in the alphabet, then that would be the case, right? You would have to branch off A, B, C, D, E, F, G, all the way to Z. But in this case, since we only have words that start with the letter A or S, we only need to branch off to A or S. Does that kind of make sense?
Yeah, but I mean the root can have multiple children.
Oh, definitely, yeah. Yeah, the root can have multiple children, yeah. That's what starts us off. All right. So let's say, for example, just like, I guess to internalize the code implementation, if we had this small little try example here, A-L-E, ale, we see that this first node, A, its information from our code would be that its character is A, its is key is true, right? It's purple, so it is a word on its own. A is a word in our list for this example. And its next map holds that the letter A points to this node L, right? The information for that is that its character is L, its is key is false, so it's white. Al isn't a word in our list. Points to the next node E, right? So ale is key, is true, is purple, so it's ale is a word in our list. And then it points to nothing. Does that kind of make sense? Everyone on the same page? Awesome. All right, perfect. Okay, so this isn't really going to be, you know, too important, but it's good to think about. Let's say you wanted to implement a try that also stored how many of the same word or same name we had in our list. All right, so far we've only talked about, I guess, like set implementations, all right, where you can't have the same word twice. You have to have unique words. But let's say both I, Sonia, the person, and Sonia the hedgehog wanted to be in the same list, and we wanted to actually like count that there was 2 Sonias in our list. We could just add an extra field, private int word count, and every time we see that we've fallen into a purple key, we've fallen into the same purple key, we just increment our word count. So if, Sonia the hedgehog, she walks, S-O-N-I-A, lands on A, increments the word count. Then I walk, S-O-N-I-A, lands on the same A, increment the word count. So we have 2 Sonias, right? Okay, questions? Yes?
What's the use of the trial? Seems like the runtime might be crazy.
The runtime is actually not too crazy. The runtime is all the operations, at least all the common operations for a try, are all in linear time. So even with space complexity and time complexity, that's actually what makes the try so effective, is because it runs in linear time. If you would imagine for us to find every word in our try, we'd only have to go through every node once. Does that kind of make sense? But of course, we're also going to go into this a little bit later, so don't worry about it too much. Any other questions? All right. Question time. Okay, this isn't for any participation grade or anything, but it's really important to know. So turn to your neighbor or think by yourself and try to answer this question on the tree or on the slide. So I'm thinking in trees. So does the structure of a try depend on the order in which strings are inserted? So if we inserted Sonia before Sonic, would that change the structure of the try or not? All right. So break off, and then we'll come back a few minutes. All right. right. I think conversations are starting to die down, so let's bring it back. Okay, what do people think? Does the structure of a trie depend on the order in which strings are inserted? What do people think? Anyone want to raise their hand and answer? Yes.
No.
Do you have a reason why?
Yeah, because it depends on like which nodes are designated as end nodes.
Mhm.
It doesn't matter what order you put them in, because you could do like A and then all, or like all and then A, and then you'll still end up with A and L already.
Yep, that's exactly it. Did everyone get that? Everyone get the same answer? Yep. Oh, yes.
I actually have one question. So if, could you go back like some slides?
Yeah, sure.
Yeah, oh yeah, that's right. Because you're using Mac, right? So
Yes.
my question is, why don't you just use private tree node next?
You can actually do that too. You can use multiple implementations, but that's really good thinking, yeah.
Okay.
There's just one type of implementation, but yeah, that's definitely possible. Any other questions? Any other questions? Okay, awesome. Thank you for asking. What am I saying? Thank you for asking and thank you for answering. There we go. Okay. Okay, so now let's get into prefix matching. We talked a little bit about what a prefix is before, but just to define what a prefix is, it's basically what the beginning, some beginning letters, characters of a string are, right? So back to the, again, Sonia Sonic example, they had the same prefix of S-O-N-I, Sony, right, at the beginning of their words, the names. Okay, so the reason why the trie, and to answer the previous question a little while ago, the reason why the trie is so appealing and so powerful is because of prefix matching, right? That's why it's used in natural language processing and word parsing so much, is because it's really, really fast and efficient when it comes to finding prefixes or finding certain patterns in words and characters, right? So, for example, there's one operation called longest prefix of, right, which finds the longest prefix of a certain word. So let's say we wanted to find in our trie what is the longest prefix we can have of the input word sample, right? So we'd go in, we'd see, all right, let's find the S, all right, then we find A, we have it. We find the next letter is M, find M. But then when we go down M, we only have an E, we don't have the P. So we return the longest prefix, the longest path that we could go down when finding the word sample, which was Sam, all right? So that's what we return. Same with find prefix, right? So prefix matching, that's another operation we have. If we input SA, if we input saw, then we're gonna output every word in our trie with the prefix, right? That beginning string saw, SA. So we have SA, right? We go down here, we have SA, we have D, sad, Sam, same, and sap. So we return all those, right? Okay, so let's imagine an algorithm that collects all the keys in a trie, right? It could be implemented as follows. So, thinking about it in English, if I had to describe an algorithm to you in plain English, I would first want to create some empty list of results that will hold all our keys in our trie, all the words in our trie. All right, and for each character in our trie, right, starting from the root, for each character in our trie, I'd call some helper function, right, that would go all the way down and actually like search for each of the purples, right, or for each of the words in our trie, okay? So how could we define this recursive method call help, right? That's what we'll call it, this helper function, call help. How can we define it? So we need a few parameters to help keep track of everything. One is the string S, which is going to hold our strings so far in the path that we've gone down. So for example, if we were going to call help on A, it would hold our previous, or I guess it would hold A, right? So if we called it on, if we inputted A into our call help, it would have A as the string. But if we called it on W, it would have AW, it would have that string, right? Because it's keeping track of all the, I guess like our path through the strings we've gone so far, or the characters we've gone so far as a string, right? Then we'd have the list X, which, okay. Then we'd have a list of string X, which is our results string, right? So it's the list of all these strings so far that we want to collect, right? So it's basically this list right here, but as we are building it. And then finally, we have our node N, which is the node that we want to call help on, right? It's the we want to call it on our children to make it recursive, to make it go all the way down. Okay. So then finally, inside call help, we'd first check, all right, if this node that we're currently on, if it's purple, if it's a key, we add it to collect. All right. If it's not, then we don't. And then for each character C in our children, we call help with, our current string so far, which so far is A, plus C, which is, or I guess it would be like nothing plus A, which is A. All right. And then X, which is our current list so far, which, in this case would be just the word A. And then we call next W. So that we'd input the W node in here. All right. So that is kind of confusing. Let's look at a better example. Okay. So if we were going to call this call help function on this whole try, all right, we want to call the collect function. We'd first go down, we'd see we have A, it's a purple node, all right, so we input it, and we go down, AW, so in our string that we input down our path, we have AW, we have the same, X, which is just A so far, we input W, all right, all right, then we input L, our next node, we have AWL so far, input our next node, our child node, we have AWLS, we see it's purple, so we put in AWLS in X, and that's what we have so far when we call it on the left leg. Then we can continue with the right leg. Again, we go down, S, SA, saw, SAD, sad, SAM, SAM, same, and SAMP. And then you can see that when we are finished with the collect method, our resulting list is all our words in the exact same order that we went through the try, right? So we went through A first, like the top left, from the top left to the bottom right, which is usually how we go through trees, left to right. Wait, any questions so far about that? Collect, call help. That makes sense? Oh, yes.
What do you return for this method? Return to collect all the.
So that's a really good question. We don't, I guess we would have a base case if we want to expand this function a little bit more. We'd have a base case that would be if we don't have any other children left, then we return whatever X is so far. Does that kind of make sense?
Yeah, but you need to return when you reach, once you find out that this key is true.
You would add it to the list once you find that it's true. So you'd add it to X.
Okay.
Awesome. Any other questions? All right, thank you for asking question. Pink shirt guy. All right. So just to recap as a summary, a try data structure implements the dictionary and set ADTs, but you can also have many other implementations as this question was raised previously. You could store your sequences using hash map, tree map, any dictionary with nodes, or within the nodes. You can even have much more exotic variants to change the try's representation, such as the ternary search try. If you're really curious, you can search about that later. But But what's really cool about tries and what the main idea is that they store sequential keys, right? So if you have a big key, you can break it up and store it sequentially, and it's a really effective tool of organizing your words and your strings like that. And again, it enables very efficient prefix operations like find prefix, which runs in linear time. Okay, interview question prep / also like real world applications of tries. Anytime after this lecture, anytime you see a word / letter parsing problem in an interview, your mind needs to immediately go to tries. You need to immediately think of tries and using tries, okay? They have very, very fast runtimes with quick word and letter lookup operations. And not just for interview, but like also for real world applications. If you want to go into software engineering or research in like NLP and stuff like that, tries. Any character sequencing problems, tries. Doesn't have to be letters, tries. Okay. Also, for interview prep, tries are interviewers' favorite like gimmick question. So it's not like tries aren't necessarily a common problem overall in interviews, but they are a very common trick question out of all the trick questions in interviews. All right. In fact, it came up for me, and I'm so lucky that I knew about tries because I used it, and I used my trap card. If anyone plays Yu-Gi-Oh, I use my trap card against the interviewer. And yeah, and I won't say what, I guess I technically am not allowed to say what interviewer it was for, but let's just say their name rhymes with Schmoogle, okay? I hope I don't get fired for saying that. But anyways, here's an example problem that I put, and it's already linked in the slide, so you can click on it and go through it yourself after this presentation. But it's a really good problem that was very similar to the problem I had for the Schmoogle interview. It's finding the first K maximum occurring words in a given set of strings, and I highly encourage you to use tries with this interview problem. All right, see if you can do it on your own. All right, finally, with that being said, any questions? Final thoughts? Yes. See, if they're not linked in the calendar, I'll just post them on EdSTEM. Oh, good. Questions? Any other final questions? Any final thoughts? Comments, concerns? If not, then I think we can head out like 10 minutes early. No? All right. Happy Friday, everyone. Don't forget your simulated midterms, okay?